Hi there, this is Jacob Nash, Algebra Lessons, and this is Unit 7, Lesson 6. This is on log n ln, as some call it. So, we have to know these now. You may or may not, I didn't mean to do that. You may or may not have learned about these, but odds are you've probably seen them on a calculator and wondered what they are. And now we're learning about a function that has this. Now, it's not very easy to understand what these mean unless you've seen, if you understand the concept of inverse functions discussed in lessons 1, 2, and 3. Remember, they have points that are opposites of each other, and they have symmetry over the y equals x axis. And that's what logarithm and exponential functions have. We learned about exponential functions, but now we're looking about logarithm. But there's also ln, which is still logarithm, but it's called the natural logarithm, and we'll learn what that means in a minute. So as I said, log is logarithm, and the pretty much parent function for this function is y equals logarithm of base b of x. So that might be kind of strange, but really what this means is b to what power equals x. So have you ever had a situation where you had something like 2 to what power equals, let's say, 8? Obviously you might know x would be 3, but how could you find this mathematically? We can see that in this case 2 and b are the same, and x and 8 are the same. So let's just change this to, well, we can just really don't need to do that. We can just say logarithm of base 2, 8. And that would also give us our answer if we were to type that into a calculator, which I'll have to tell you how to do that because it's more complicated than you might think. So that's what that statement really means. When we're having a logarithm, we're seeing something to what power equals something else. So it's the opposite of exponential functions. Another way to think about this, like I said, it's the opposite of exponential functions. So just as a quadratic and square root function are opposites, not necessarily opposites, but they're inverses, so are, well, actually, that's not really correct. They are, to some degree, inverses. Really, it would be this, because as we know, that looks like that, and if we only had that, it would be like that, but there's really that also. So, just as those are inverses, so are logarithm and exponential, which I told you that the parent function was really this. I guess so, but really we could just say that 2 is b because that's the base. And then again, we'll see that we can make b2 for the parent function and when we're graphing these. But now let's see, what is ln, logarithm? It's the same as log, but it has a base of e. So we know that we had a base of b for logarithm, as we can see, base of b, but we have a base of e. So you might think, okay, but what the heck is e? So e is not a variable like b is. B can be replaced with any number, but e is a, basically it is a mathematical thing like pi. Pi is always 3.14, whatever. Same thing with this. E equals 2.71, 828, 1828, whatever. But, anyways, if you ever have a base of e, then the answer is going to be something that is a constant number, which is a number that has so many decimals that it goes on forever. Here are examples of e bases. Pi, that doesn't mean that these are e, it means that they could be answers if E was the base. So then we have pi. We know that goes on forever, 3.14592, or sorry, actually, I think it's this. I don't know that much of it, but that goes on forever. If you were to try to figure it out, that would go on forever. Then this random number, 2.1847, not going to say that all. And then to hint that it goes on forever, we have those dots right there. Then we have -2. Although -2 doesn't seem to go on forever, it is still considered a constant because there are no such things as a logarithm of a negative number. If you try to type that into a calculator, it will say that's not a thing that you can do. Then we have 4/7 and 1/9. So what is 4/7? 4/7. Where's my calculator? Because I don't know that off the top of my head. Hang on. Okay, it is 0.57142, etc. I don't know if it actually, I should just add an 8 onto that. I'm pretty sure this is the pattern that it follows. It just repeats those 6 digits. So therefore, that would also be an answer with the E base, which means that this would be a ln natural logarithm function, not just a log function. Then 1/9, this is 0.1 repeating, and although you just have the same digit over and over, still that is a, you could really just say that it's this, and then just say that, but most people, when it's a number that repeats, they put a line over it like that. So those are all examples of that. So, which of these bases would be natural logarithms and just normal logarithms? So if you had a base of 2, well, this actually isn't the correct thing to say. It's these wouldn't be the bases. These would just be the pretty much simplifications of the expressions, because like I said, E equals this. So 2, if we had 2 as an answer, basically we're asking ourselves, is it a constant? No. Logarithm? Yes. Natural logarithm. Is this a constant? Do the decimals go on forever? No. So this is a logarithm function. That's a evaluation of that. Pi, that does go on forever, so ln. Since this has 3 dots, ln. 2.3 doesn't go on forever, log. 2/3, it is 0.6 repeating, or sometimes it's usually rounded to that, but hopefully you know that it's just 6 repeating, so that would also be a ln function. -3, since it's negative, ln. Square root of 17, that is not a perfect square root. We get 4.123, etc. So that would be a ln function. And then the square root of 442 is also not a perfect square. If it was 441, it would be, but it's 21 point whatever. So most of these we've seen are like that. That doesn't mean that more are. These were just examples. So solving them. Okay, well, you can solve these. Basically, this just means you can figure out what x is in certain situations. And there's not necessarily steps that can apply to every problem, but basically what that thing is saying is that you just use this. If you're trying to figure out what x is, you need to see 3 values and then just change them to this. So we can see for number 1, what would our a be? Our a would be 2, so we just will put 2 here. What would our c be? C is right here, so c is x. Then we have 16, which is going to be our b. Okay, so now we can see that, honestly, if you didn't know what this was, you wouldn't get very far, because in a situation like this, since x is by itself, then the thing you would do was just type this into the calculator. But if you have it set up like this, you wouldn't have to type it into the calculator because you would know that x is 4. Because, well, really, what you can do is take any root of this. Square root, that gives us 4, so no. Cube root, that gives us something that's not even a number that we can use. So then 4, that would be our correct answer. And that would give us 4. So that is our answer for that one. So in a situation where x is by itself, there's really no point. You pretty much would have to type that into the calculator anyways. All right, for this one, number 2, x is not by itself, so it's different. So what is our a? Our a is x, so we can put x here. Our b is 81. Or sorry, that 81 goes over here. And then our c is 4. So we put this, because of this, we put the c to the power of x to the power of 4. Now, if we're trying to find what x is, we just take the 4th root, and we get that x is 3. So that's what the answer is for that. Okay, that's not good. And I'm going to have to scroll away from that, but we'll just remember what it is. Okay, so I'll just write what our things are here. So we have a, b, and c, and remember we need to have a to the c power equals b. So that means we have 3 to the 2nd power equals x. What is 3 squared? 9. So x is 9. That was kind of a simple one. Alright, okay. Now I need to just erase this because I'm ruining this. It's because I'm left-handed and it makes it do that. Okay, now we have this one. What are we going to do here? Okay, we have something different. So, if we're... I'm kind of confused about what I was trying to do here. For this one, it doesn't appear that I'm trying to do that. I don't know why I have this. Well, actually, I'm just saying, maybe I was just trying to say that those are equal, because it doesn't matter if you have that e there, it's the same. That you can... 3 ways... Okay, that just lagged. Okay. 3 ways you can write that is if you just have ln of x, it's the same as if you write ln base e of x, or if you write log base e of x. It's the same thing. That's what I was trying to say. I don't know why I had it like that. Okay, now how do you type this into the calculator? Because if you notice, how can you type a base in there if it's what's called a subscript? As a review, whatever you have, let's just say we have x. Okay, why is it undoing something that I did less recently? I don't know. Let's say we have x. What's up there is called the superscript, and that's where exponents go. What's down here is subscript, and that's what our bases are. And so you can't type that into the calculator. As you can see, we use this button to type a superscript, but there's no subscript button. So we have to do it a different way. And this image from a video, sorry I forgot the channel name, but so I don't own this image, but it explains how to do it. So if you're just having something like log of 1000, then you can type that in. But if you have something like what we're doing with the base, what you have to do is do log over the number that's not a base, or log of the number that's not a base, divided by log of the number that is the base. And I have a formal equation for that. This thing is really lagging. See, it just takes forever, and then it undraws everything I did. So if you can't type in log base 2 of x in the calculator, it won't work. It automatically will think that you're trying to do log of 2. Obviously you can't type in x because that's not even a value. If you wanted to do something like this, it wouldn't work in the calculator like that, because it would think you're doing log this, and then it would think you're doing log 20, and it would assume your base is 10 because that's automatically what it is. So instead, if you were trying to do that, you would need to do, if we were going back to this, where we have log base 2, 10, you need to do log 10 divided by log 2. So in other words, we have this. For log A, base A of B, you need to make it log B divided by log A. That's what you do. So that's it for this video, and I'll see you on the next one about how to graph these. Thanks for watching.